Okay, let's go. Number 10, the fine structure constant. In the equations that govern how light interacts with matter, there sits a number that has haunted physicists for nearly a century. Its official designation is alpha. Its value is roughly 1 over 137. This is the fine structure constant. It determines the strength of the electromagnetic force, the force that holds atoms together, the force that makes chemistry possible, the force that keeps electrons orbiting nuclei without spiraling inward or flying apart into the void. Here is the problem. This number should not be this precise. Alpha is dimensionless. It has no units. It is not meters or seconds or kilograms. It is a pure number, the same in any measurement system anywhere in the universe. We know its value to 10 decimal places thanks to measurements by CODATA, the Committee on Data for Science and Technology. But no theory predicts why it has this value. We measure it. Electrons would spiral into nuclei. If it were 1 over 138, atoms would fly apart. The electromagnetic force would be too weak to hold matter together. No stable atoms. No periodic table. No chemistry. Wolfgang Pauli spent the last years of his life obsessed with this number. He filled notebooks trying to understand why 137. Richard Feynman called it a magic number, a number that comes to us with no understanding. He wrote that all good theoretical physicists put this number on their wall and worry about it. Why this number? Why not 1 over 100 or 1 over 200? Out of an infinite range of possible values, the universe selected roughly 1 over 137, and it selected it with extraordinary precision. The consequences of this precision are total. Every atom in your body depends on alpha being exactly this value. The way light reflects off surfaces, the way molecules bond, the way stars burn hydrogen into helium. All of it is calibrated to this number. Change alpha by 1 part in 1,000 and stellar fusion stops working. Stars never ignite. The universe remains dark and cold. This is not a coincidence. This is not an approximation. This is a fundamental constant of nature measured to 10 decimal places, and we have no idea why it has the value it does. Alpha is just the beginning. If one constant is suspiciously precise, perhaps it is an outlier, a statistical fluke. But when you look at the next number, the pattern becomes impossible to ignore. Number 9, the cosmological constant, lambda, the energy density of empty space, the force that is accelerating the expansion of the universe, tearing galaxies apart, driving everything away from everything else. This is the most precise number in physics, and the most wrong. Here is what we measure. Lambda has a value of approximately 10 to the negative 122 in Planck units. This is the observed energy density of the vacuum, confirmed by observations of type Ia supernova in 1998, by measurements of the cosmic microwave background, by the large-scale structure of galaxies. Dark energy, as we call it, makes up 68% of the universe. Lambda describes its strength. Here is what quantum field theory predicts. The vacuum is not empty. It seethes with virtual particles, quantum fluctuations popping in and out of existence. These fluctuations have energy. When you calculate how much energy, you get a number. That number is 10 to the 120th times larger than what we observe. 120 orders of magnitude. Off. This is the vacuum catastrophe. It is widely considered the most embarrassing failure in the history of theoretical physics. The prediction and the measurement disagree by a factor of 1 followed by 120 zeros. To put this in perspective, if you tried to measure the circumference of Earth and you were off by the width of a single atom, you would still be infinitely more accurate than this calculation. If the quantum prediction were correct, the universe would have ripped itself apart in the first fraction of a second after the Big Bang. Space would have expanded so violently that no structure could form. No galaxies, no stars, no atoms, just a thin soup of particles flying apart faster than light. But the universe did not rip itself apart. We are here, which means lambda is not 10 to the 120th. It is 10 to the negative 122. The vacuum energy is tuned to a precision of 1 part in 10 to the 242nd. There is no theory that explains this. Quantum field theory and general relativity, the two pillars of modern physics, are fundamentally incompatible at this point. One says the vacuum should be violently energetic. The other says it is almost perfectly calm. Both cannot be right. Yet we need both to describe reality. The precision required for lambda to have its observed value is beyond comprehension. It is not like hitting a target. It is like throwing a dart at a board the size of the observable universe and hitting a specific atom. And the universe hit that atom. Alpha was precise. Lambda is impossibly precise. Two constants, two knife edges, but constants exist in isolation. When you look at the relationships between different forces, the fine-tuning becomes a conspiracy. Number 8, the electromagnetic gravitational force ratio. 10 to the 36 to 1. The electromagnetic force is 1 trillion times stronger than gravity. This is not a theoretical prediction. This is a measured fact. Two fundamental forces, completely independent in their origins, separated by 36 orders of magnitude in strength. This ratio has no right to be stable. Electromagnetism holds atoms together. It binds electrons to nuclei, creates chemical bonds, makes molecules possible. Gravity holds planets together. It ignites stars, forms galaxies, shapes the large-scale structure of the cosmos. These forces operate in different domains. They should have nothing to do with each other, but they are balanced, precisely balanced. Gravity is weak enough that chemistry can happen. Atoms do not collapse under their own gravitational attraction. Molecules can form. Complex structures can exist. But gravity is strong enough that gas clouds collapse into stars. Stars ignite. Make gravity stronger, and stars burn through their fuel in years instead of billions of years. Planetary systems never stabilize. Life has no time to evolve. Make gravity weaker and gas clouds never collapse. Stars never form. The universe remains dark. The ratio is not just stable, it is optimized. Main sequence stars like our sun burn for 10 billion years because of this ratio. Red dwarfs burn for trillions of years. This gives planets time to form, atmospheres time to stabilize, chemistry time to become biology. Here is the disturbing part. This ratio depends on multiple independent constants. The strength of electromagnetism is set by alpha, the fine structure constant. The strength of gravity is set by the gravitational constant g. These are separate numbers, measured independently with no known relationship. Why would they coordinate? Why would two unrelated forces know about each other? Stellar evolution models show the precision required. If the ratio were 10 to the 35 to 1 instead of 10 to the 36 to 1, stellar lifetimes drop by a factor of 10. If it were 10 to the 37 to 1, stars never reach the temperatures needed for carbon fusion. The periodic table stops at helium. This is not one constant being precise. This is two independent constants being precisely coordinated to produce a specific outcome. A ratio that allows stars to burn long enough for planets to form, for chemistry to complexify, for observers to emerge. Three numbers, three impossible precisions. But there is a number that makes physicists more uncomfortable than any other. A number that was predicted before it was measured, based purely on the requirement that we exist. Number 7, the carbon resonance level. 7.656 megaelectron volts, the resonance energy of the carbon-12 nucleus. This number was reverse engineered from the fact that you are made of carbon. In 1953, physicist Fred Hoyle was studying stellar nucleosynthesis, the process by which stars forge heavy elements. He encountered a problem. Carbon should not exist in any significant quantity in the universe. Here is why. Carbon forms inside stars through the triple alpha process. 3 helium nuclei must collide and fuse simultaneously. This is absurdly unlikely. Helium nuclei are positively charged. They repel each other. Getting 2 to fuse is difficult. Getting 3 to fuse at the same moment is nearly impossible. The probability is so low that stars should produce almost no carbon. Yet carbon is abundant. It is the 4th most common element in the universe. It is the foundation of organic chemistry. You are 18% carbon by mass. Hoyle realized something. If carbon exists in abundance, there must be a resonance, a quantum energy level inside the carbon-12 nucleus that dramatically increases the probability of 3 helium nuclei fusing. Without this resonance, the triple alpha process does not work. With it, carbon production becomes efficient. He calculated what energy this resonance would need to have. Based purely on the requirement that carbon exists, he predicted a resonance at 7.656 megaelectron volts. This was not a prediction from first principles. This was anthropic reasoning. We exist. We are made of carbon. Therefore, this resonance must exist at this specific energy. In 1957, experiments at Caltech confirmed it. The resonance exists at 7.656 megaelectron volts, exactly where Hoyle said it would be. This is one of the most disturbing predictions in the history of physics. Hoyle worked backward from the conclusion to the cause. He used the existence of observers to predict a property of atomic nuclei. And he was right. The precision is extraordinary. If the resonance were at 7.6 megaelectron volts or 7.7 megaelectron volts, carbon production drops by a factor of 1,000. Stars would produce trace amounts of carbon, not enough for planets, not enough for chemistry, not enough for life. But the resonance is not at 7.6 or 7.7. It is at 7.656. The exact energy needed to make carbon abundant. There is more. Oxygen also has a resonance level. If oxygen's resonance were slightly lower in energy, stars would convert all their carbon into oxygen. No carbon would survive. If it were slightly higher, carbon would accumulate, but oxygen would be rare. Complex chemistry requires both carbon and oxygen in similar abundances. The oxygen resonance sits at exactly the right energy to allow both elements to coexist. Another precision, another coincidence. Hoyle's prediction opened a door physicists wish had stayed closed. It suggested that the universe's properties can be inferred from the existence of observers, that the constants of nature are not random. They are selected by the requirement that someone must be here to measure them. 4 numbers, 4 precisions. And now a 5th number, one so precisely balanced that changing it by 1 part in a million would end chemistry. Number 6, the strong nuclear force coupling constant, alpha S, approximately 0.118. This is the number that determines how tightly quarks bind together to form protons and neutrons. It governs the strong force, the most powerful force in nature, the force that holds atomic nuclei together against the electromagnetic repulsion trying to tear them apart. Change this number by 0.5%, and atomic nuclei cease to exist. The strong force operates at the smallest scales. Inside protons and neutrons, quarks are bound by gluons, particles that carry the strong force. The strength of this binding is set by alpha S. At 0.118, the force is strong enough to confine quarks permanently. No quark has ever been observed in isolation. They are always bound in groups. This confinement is essential. If alpha S were weaker, quarks would not bind tightly enough. Protons and neutrons would fall apart. If it were stronger, quarks would bind so tightly that all matter would collapse into exotic particles. No hydrogen, no atoms, no chemistry. The viable range is narrow, between 0.117 and 0.119. Outside this window, nuclear physics breaks down. Lattice quantum chromodynamics calculations show the precision required. At 0.117, the deuteron, the simplest nucleus after hydrogen, becomes unbound. Deuterium does not exist. Stars cannot fuse hydrogen into helium. Stellar nucleosynthesis stops at the first step. At 0.119, the strong force becomes so powerful that protons bind to protons directly. All hydrogen in the early universe fuses immediately into heavier elements. No hydrogen survives. No water. No organic chemistry. The universe sits at 0.118, exactly in the middle of the viable range. If you assume this value is random, selected from a uniform distribution of possible coupling strengths, the probability of landing in the viable window is approximately 1 in 200. Not impossible, but unlikely. Here's where it gets worse. The strong force does not operate in isolation. It must be tuned relative to the electromagnetic force. If the electromagnetic force were slightly stronger, it would overpower the strong force. Nuclei would fly apart. If it were slightly weaker, nuclei would collapse under the strong force. These are independent parameters. Alpha S is set by quantum chromodynamics. Alpha, the fine structure constant, is set by quantum electrodynamics. They are measured separately. They have no known theoretical relationship, yet they are coordinated. The ratio between them allows nuclei to be stable. Protons and neutrons bind together, but not so tightly that all matter collapses. Not so loosely that nuclei disintegrate. This is the multi-parameter problem. It is not enough for one constant to be precise. Multiple constants must be precise simultaneously, and they must be precise relative to each other. The probabilities multiply. If alpha S has a 1 in 200 chance of being in the viable range, and alpha has a 1 in 1,000 chance, the combined probability is 1 in 200,000. Add more constants and the odds become astronomical. 5 numbers, 5 knife edges, but the next number is different. It is a mass difference at the quantum scale tuned to a fraction of a percent, and it is the only reason chemistry exists. Number 5, the neutron-proton mass difference, 1.29 megaelectron volts. The neutron is 0.14% heavier than the proton. This tiny difference is the only reason chemistry exists. Protons and neutrons are the building blocks of atomic nuclei. They are nearly identical in mass. A proton weighs 938.27 megaelectron volts. A neutron weighs 939.56 megaelectron volts. The difference is 1.29 megaelectron volts, less than 0.2%. This difference determines everything. When a neutron is free, isolated in space, it is unstable. It decays. Through beta decay, mediated by the weak nuclear force, the neutron transforms into a proton, an electron, and an antineutrino. The half-life is 15 minutes. Free neutrons do not last long, but inside a nucleus, neutrons are stable. Bound to protons by the strong force, they do not decay. This is why atomic nuclei can contain neutrons. This is why elements heavier than hydrogen exist. The mass difference sets the boundary between stability and decay. At 1.29 megaelectron volts, the balance is perfect. Neutrons decay when free but remain stable when bound. This allows nuclei to form. This allows the periodic table to exist. Change this number, and the universe breaks. If the mass difference were 1.5 megaelectron volts instead of 1.29 megaelectron volts, neutrons would decay faster. Even inside nuclei, they would be unstable. Beta decay would occur rapidly. All neutrons would transform into protons. Atomic nuclei would consist only of protons, but protons repel each other electromagnetically. Without neutrons to provide binding through the strong force, nuclei would fly apart. No elements heavier than hydrogen, no carbon, no oxygen, no iron. The periodic table stops at element 1. If the mass difference were 1.0 megaelectron volts, the opposite occurs. Protons become heavier than neutrons. Now protons decay into neutrons. Through inverse beta decay, protons transform into neutrons, positrons, and neutrinos. All hydrogen in the universe converts to neutrons. Neutrons do not form stable nuclei on their own. They decay. The universe becomes a sea of decaying neutrons. No atoms, no chemistry, no structure. The viable window is narrow, between 1.2 and 1.4 megaelectron volts. Inside this range, both protons and neutrons can exist in stable nuclei. Hydrogen survives. Heavy elements form. Chemistry becomes possible. The universe sits at 1.29 megaelectron volts, in the middle of the window. This is quantum scale precision. The mass difference arises from the masses of the up and down quarks that compose protons and neutrons. These quark masses are fundamental parameters of the standard model of particle physics. They are measured, not derived. We do not know why they have the values they do, but we know the consequences. Change the up quark mass by 1% and the neutron-proton mass difference shifts outside the viable range. Change the down quark mass by 1%, same result. The precision required is less than 1 part in 100 at the most fundamental level of matter. 6 numbers, 6 knife edges. At this point, physicists start using a word they hate, a word that implies intention, design, purpose. But there is a number that forces even the most skeptical scientists to confront this word directly. Number 4, the Higgs field vacuum expectation value, 246 gigaelectron volts, the vacuum expectation value of the Higgs field. This number gives mass to everything, and it is balanced on the edge of catastrophe. On July 4, 2012, physicists at the Large Hadron Collider announced the discovery of the Higgs boson. This confirmed a theory proposed in 1964 by Peter Higgs and others. The Higgs field permeates all of space. It is not empty space. It is a field with a non-zero value everywhere in the universe. Particles gain mass by interacting with this field. The stronger the interaction, the more mass. Electrons interact weakly. They have little mass. Top quarks interact strongly. They are heavy. Photons do not interact at all. They have no mass. The strength of the Higgs field is set by its vacuum expectation value, 246 gigaelectron volts. This is the field's resting state, its baseline energy density throughout space. At this value, particles acquire the masses we observe. The electron gets 0.511 megaelectron volts. The top quark gets 173 gigaelectron volts. The W and Z bosons get 80 and 91 gigaelectron volts. Change this number, and particle masses change. Change it significantly, and the universe becomes unrecognizable. But there is something more disturbing. At 246 gigaelectron volts, the universe is metastable. It is not in its lowest possible energy state. It is in a local minimum, a valley in the energy landscape, but not the deepest valley. There is a lower energy state available, the true vacuum. Vacuum stability calculations show the problem. With the Higgs boson mass measured at 125 gigaelectron volts and the top quark mass at 173 gigaelectron volts, the universe sits in a metastable configuration. The current vacuum could tunnel to a lower energy state through quantum fluctuation. This is called vacuum decay. If vacuum decay occurs, a bubble of true vacuum forms. Inside the bubble, the laws of physics are different. Particle masses change, atoms disintegrate. The bubble expands at the speed of light, converting everything it touches. There is no warning, no defense. The bubble wall is the end of everything. The probability of this happening is extraordinarily low. The universe has existed for 13.8 billion years without decaying, but the fact that it is possible at all is unsettling. We live in a universe that is stable enough to last billions of years but not fundamentally stable. If the Higgs vacuum expectation value were 250 gigaelectron volts instead of 246 gigaelectron volts, the metastability becomes instability. The universe would have decayed long ago. If it were 240 gigaelectron volts, the universe is more stable, but particle masses shift. The W boson becomes lighter. Electroweak interactions change. Stellar nucleosynthesis is disrupted. The window is narrow, between 244 and 248 gigaelectron volts. Inside this range, the universe is metastable but long-lived. Particles have the right masses. Chemistry works. Star burn. This is where physicists started using a word they hate: fine-tuned. In published papers in peer-reviewed journals, the term appears. The Higgs vacuum expectation value is fine-tuned, not as a metaphor, as a technical description of the precision required. 7 numbers. 7 precisions. The word fine-tuned is now unavoidable, but there is a number that goes beyond fine-tuning. A number that appears in so many unrelated contexts that it suggests the universe is speaking a mathematical language. Number 3, dimensionless physical constants. 1 over 137, 1 over 128, 1 over 100. Across the landscape of fundamental physics, dimensionless constants cluster near the same scale. The universe appears to have a favorite number. Dimensionless constants are pure numbers. They have no units. They are not meters or seconds or kilograms. They are ratios, relationships between fundamental quantities. They are the same in any measurement system anywhere in the universe. An alien civilization using completely different units would measure the same dimensionless constants we do. Alpha, the fine structure constant, is 1 over 137. The weak mixing angle, also called the Weinberg angle, is approximately 0.23, or roughly 1/4. The ratio of the electron mass to the proton mass is 1 over 1836. These are unrelated constants. They govern different forces, different particles, different domains of physics. There is no known theoretical reason why they should have similar magnitudes, yet they cluster. The fine structure constant is near 1 over 100. The weak coupling constant is near 1 over 30. The strong coupling constant at low energies is near 1 over 10. These are order of magnitude neighbors. They sit in the same range of the number line. Why? Why not 1 over 10,000 and 1 over 1 million? Why not 1/2 and 1/3? Out of all possible values these constants could take, they cluster near 0.01 to 0.1. The universe uses this scale repeatedly. No theory predicts this clustering. The standard model of particle physics takes these constants as inputs. They are measured, not derived. We plug them into the equations. The equations work. But we do not know why the constants have the values they do, and we do not know why they cluster. This pattern forces a confrontation. Physicists are left with 3 explanations. All 3 are uncomfortable. Explanation 1, the multiverse. Our universe is one bubble in an infinite foam of universes. Each bubble has different constants. Most bubbles are sterile, lifeless, unable to support structure. We exist in a bubble where the constants happen to cluster in a life-permitting range. This is selection bias. We observe these values because we could not exist in a universe with different values. Explanation 2. Simulation. We live inside a computational system. The constants are set by a process or entity with the goal of producing observers. This is the design hypothesis. The universe is not random. It is calibrated. All 3 explanations are unfalsifiable. The multiverse cannot be observed. The simulation cannot be tested from inside. Design cannot be proven without access to the designer. Science operates on falsifiability. These hypotheses lie outside the reach of the scientific method. This is the philosophical crisis. Physics can describe what the constants are. It cannot explain why they are. And when the clustering becomes undeniable, when the pattern is too strong to ignore, physicists are forced to choose between 3 explanations that all violate the principles of science. 8 numbers. 3 impossible explanations. Physicists are trapped. They can calculate the odds of these numbers arising by chance. And the odds are so astronomically small that the calculation itself becomes meaningless. Number 2, the combined probability. 10 to the negative 229. The probability that all fundamental constants land in life-permitting ranges by chance. This number is so small it has no physical meaning. Physicists have attempted to calculate the odds. Take each constant. Determine its viable range, the window within which the universe can support structure. Calculate the probability of landing in that window if the value is selected randomly. Then multiply the probabilities together. Alpha, the fine structure constant, has a viable range of roughly 1 in 1,000. The cosmological constant has a viable range of 1 in 10 to the 1/20th. The strong force coupling constant has a viable range of 1 in 200. The neutron-proton mass difference has a viable range of 1 in 100. Multiply these together. Add the probabilities for the electromagnetic gravitational force ratio, the carbon resonance level, the Higgs vacuum expectation value, and the clustering of dimensionless constants. The combined probability is approximately 1 in 10 to the 229th. This is a 1 followed by 229 zeros. To put this in perspective, there are roughly 10 to the 80th atoms in the observable universe. The probability we are discussing has more zeros than there are atoms in all of existence. It is a number so large that it cannot be visualized, cannot be comprehended, cannot be given physical meaning. Calculations of this type have been published by physicists John Barrow, Frank Tipler, and Martin Rees. They are not fringe speculation. They are peer-reviewed attempts to quantify the fine-tuning problem, and they all arrive at the same conclusion. The odds are incomprehensibly small. Physics cannot work with probabilities this extreme. In any other context, the probability of 1 in 10 to the 229th would be treated as impossible. If you flipped a coin and it landed on heads 229 times in a row, you would not conclude you were lucky. You would conclude the coin was rigged. But the universe is not a coin, and this is where science breaks down. The anthropic principle offers one response. We exist. Therefore, the probability is not 1 in 10 to the 229th. It is 1. We are here. The constants must have landed in the viable range because if they had not, we would not be here to ask the question. This is observer selection bias. We can only observe universes where the constants permit observers. This sounds like giving up. It abandons explanation. It replaces why with because we are here. The multiverse offers another response. There are infinite universes, each with different constants. In an infinite ensemble, every possible combination occurs. Somewhere, a universe has constants that permit life. We exist in that universe. This is not luck. This is statistics over infinite trials. This sounds like science fiction. It invokes unobservable entities to explain observations. It is unfalsifiable. Both responses abandon traditional scientific explanation. They replace mechanism with selection. They replace causation with anthropic reasoning. This is an intellectual failure. Physics is left without a satisfying answer. 9 numbers, 1 impossible probability. But there is a final number that makes all of this personal. A number that suggests you are not just observing the fine-tuning. You are evidence of it. Number 1, the Bekenstein bound, 2.58 times 10 to the 43rd bits per kilogram per meter. The maximum information density allowed by the laws of thermodynamics. You are an information structure that should not be thermodynamically possible. In 1981, physicist Jacob Bekenstein derived a fundamental limit on how much information can be contained in a given region of space with a given amount of energy. This is not a technological limit. This is a limit imposed by the laws of physics themselves. Cram too much information into too small a space and it collapses into a black hole. The Bekenstein bound sets the maximum. For any physical system, the information content cannot exceed 2.58 times 10 to the 43rd bits per kilogram per meter of radius. This is the thermodynamic ceiling. Above this limit, entropy overwhelms structure. Information is destroyed. Your brain contains approximately 86 billion neurons. Each neuron connects to thousands of others through synapses. There are roughly 10 to the 15th synaptic connections in your brain. Each synapse can be in multiple states, encoding information. Conservative estimates place the information content of a human brain at 10 to the 16th bits. You are a low-entropy structure. You are organized. You are complex. You are an island of information in a universe that trends toward disorder, toward maximum entropy, toward heat death. The second law of thermodynamics says entropy increases. The universe moves from order to chaos. Stars burn out. Structures decay. Information is lost. Yet here you are. A structure that maintains itself, that processes information, that observes. For you to exist, the fundamental constants must allow information structures to form below the Bekenstein bound. The constants must permit atoms to be stable, molecules to be complex, chemistry to be rich enough to build self-replicating systems, brains to store and process information without collapsing into thermodynamic equilibrium. This requires all 9 previous numbers to be precise. Alpha must be 1 over 137 so atoms hold together. Lambda must be 10 to the negative 122 so the universe does not tear itself apart. The electromagnetic gravitational ratio must be 10 to the 36 to 1 so stars burn long enough for planets to form. The carbon resonance must be at 7.656 megaelectron volts so complex molecules exist. The strong force must be 0.118 so nuclei are stable. The neutron-proton mass difference must be 1.29 megaelectron volts so chemistry is possible. The Higgs field must be 246 gigaelectron volts so particles have the right masses. Dimensionless constants must cluster so forces are coordinated. And the combined probability must be defied. You are not observing the fine-tuning. You are the fine-tuning. Your existence is the evidence. Every thought you have, every observation you make, every question you ask about why these numbers are what they are, all of it depends on these numbers being exactly what they are. You are the outcome of the precision. You are the structure that the constants permit. This is the observer selection effect taken to its logical conclusion. The universe does not just permit observers. The universe's properties can be inferred from the existence of observers. You are reading this because the fine structure constant is 1 over 137. You are thinking about this because the cosmological constant is 10 to the negative 122. You exist because 10 numbers are too perfect to be an accident. These perfect numbers are either the universe's deepest secret or its most elaborate illusion. They form interconnected web of precision, each parameter sitting exactly where it needs to be for atoms, stars, galaxies, and life to exist. We exist in a universe that appears designed for observers. We do not know why. We may never know why. The numbers are too perfect to be an accident, but we cannot prove they are anything else. If you want to see more videos like this, subscribe for more.